So we have like two wonderful speakers. So first one is Adrienne Kline. She is professor in the Department of Surgery and Electrical Computer Engineering at Northeastern University. Her work includes developing both novel methodology and takes a mathematical and domain-agnostic approach to contributions to computer science and engineering, as well as developing novel applications to solve health problems while emphasizing integrations into clinical workflows. And then we have as well Chinmay Rane, who has a PhD in neural networks and deep technical expertise in designing, developing, and optimizing AI algorithms for imaging, large language models, and multimodal applications. His current work focuses on building innovative and intuitive medical imaging solutions, leveraging MONAI to advance healthcare and life sciences. Very looking forward. Over to you.
Thank you.
Hello. Hi, I'm Adrienne. So I am dually trained, as kind of mentioned in our intro, in both engineering and medicine. And so after my PhD, I went to medical school. And today I get the privilege of showcasing why it was a really easy decision to leave medicine and go back to engineering world and develop some of the amazing technology. So here's a great example in how we're revolutioning cardiac diagnosis with AI, including a MONAI-based MRI segmentation framework. So at my lab at Northwestern University, we work on developing state-of-the-art AI that is informed by raw medical imaging or clinical data to perform actionable insights into clinical care. So in other words, we develop technology that to see what and how doctors do, and sometimes what they don't. So today I have the privilege of introducing our amazing team and unveiling the vision for this project, as well as kind of opening up the clinical problem and how this serves an important need, as well as the technical challenges and hurdles that we faced in building this. Chinmay and I are both going to overview the MONAI-based solution in terms of how we actually solved some of these problems, as well as the road ahead, and then open up for Q&A. So, introducing our amazing team. So, it comprises of the Kline Engineering Lab, as well as some of my clinical collaborators who are here with us today at the university. It obviously includes Quantify here, which included some more engineering software engineering support, and NVIDIA, who provided the MONAI deep learning framework and GPUs whose jobs these all ran on, as well as the AWS framework that allows for the scaling and flexibility of the cloud in terms of hosting these amazing solutions. So, leading off, the leading cause of death in the US and globally is cardiac disease. So this is responsible for 1 in 5 deaths that occur every 33 seconds and costs the US over $250 billion annually alone. Currently, there are 6.2 million Americans living with heart failure, and unfortunately, this number is only expected to increase. So I want to showcase why what we're going to be doing is a fundamental shift in how we're actually going to be looking at some of the diagnostic imaging to help with this problem. So, cardiac care, one of the big methods and data streams for assessing a person's cardiac state includes multimodal imaging. So this includes cardiac MRI, CT, coronary angiograms, ultrasounds, but we had to start somewhere. So where are we going to start? I selected we would start with cardiac MRI because it's the gold standard in actually assessing how the pump part of our heart functions. The heart is a great mechatronic system where it has both an electrical system and a mechanical system, and these two have to integrate really well. So cardiac MRI doesn't suffer from the ionizing radiation that CT would, as well as we actually get to capture multiple views into the beating heart that we can't really usually get from a static single CT image. And so in the assessment of cardiac MRI, the many views are captured as a result of this, which means we need many views and many models to facilitate. So, as I mentioned, multiple views into the beating heart. So each view is going to provide specific insight into various kinds of cardiac structures, as well as their function. Traditionally in radiology, these are manually assessed. So this means that there's a radiologist sitting there at their desk and looking at these images, and they pick a point here and they pick a point there, and they take these measurements about how thick is the wall and what's the area of how much that ventricle or one of the heart chambers actually moves, and what's the volume associated with that, because that's what actually feeds into diagnoses. So I want us to teach models to do what those clinicians do, because driving segmentation abnormalities in this way actually allows us to replicate that workflow, and then this is what feeds into the diagnoses of heart failure, cardiomyopathies, which then is the indication referral for starting medications or further investigations, as well as surgery. So just to orient you, so here's a few views of the cardiac MRI. So I've kind of tried to orient you with the cartoon version of the heart so that you can kind of look at the MRI version of that, the cartoon version illustration. So you can see in the 4-chamber long axis, we can see all 4 chambers of the heart actively. And you can see here that we've actually kind of annotated with our in concert with our radiologists about this person suffering from right heart failure and has a dilated heart chamber known as an atrium. You can see in the short axis or the middle stack that there's a thickened wall. So we want to be able to actually calculate the measurements that drive that. And that's as a result, in this case, of high blood pressure. In the 3-chamber long axis, we can actually start to see some of the valves and how well these are going to be moving. And that same heart attack scar that you can see in the short axis view, you can see manifested in the 3-chamber long axis view as well. So here are 3 more views that we did this work with. And so the 2-chamber long axis, the left ventricular outflow tract, as well as the short axis aortic valve. So these are really amazing insights in terms of being high-res insight into the video versions of the beating heart. So the challenge in terms of the technical and the clinical challenges. So prior approaches are really insufficient in this regard. When we think about identifying anatomy, so something like a bounding box is really only going to give us information about where something is, not how something is. We can do whole image classification for disease diagnosis, but that means that you have to have a model for every kind of disease process that you might want to actually look at, as well as that these are a little bit more black box and not particularly explainable. And when we think about Gen AI in this regard, in the case of something like a vision language model, these processes are more correlative and not the definitive measures that we want. So in response to that, I want automated segmentation for every element in every slice and every view, regardless of source instrument or image quality. I want us to be able to detect the structures that are important. So this feeds into the disease state, the image quality, and how well this is going to run. And as I mentioned, these vision language models, multimodal, are correlative, and I think are a great first pass at an imaging assessment, but are not the kinds of definitive things that we're going to need here. So I want derivation of empirical metrics directly from those segmentation models that are second order. Moreover, the time it takes radiologists or cardiologists to look at these images and take those measurements or calculate these measurements is very time consuming in terms of their report creation. So what do we want to do? We want an automatic report creation that's detailed and customizable, where we can actually start to flag those out of bound items. So if the wall is too thick, if the heart isn't pumping as much blood every time it beats as it should. So the optimal solution is going to reproduce clinicians' processing, where we actually have a user interface we've built alongside this that has a report that's deterministically based on those segmentation maps and upcoming. So our approach in this regard, so as I mentioned, we want to limit the number of annotations we actually have our radiologists and cardiologist trainees and fellows do. So in order to do that, we need to run really lean, because there was no data set in order to do this. I had the raw data and that was it. So in response to that, we have to use self-supervised learning models to decrease the number of annotations that we're actually going to use to build this kind of a model. This means that we want to incorporate state-of-the-art transformer models, and it is through the partnership between my lab as well as AWS and Quantify, who we're going to hear from shortly, that made the solution possible. So I'm going to hand it over to the amazing Dr. Rane from Quantify to talk through our architecture.
Yeah. So thank you, Dr. Kline, for that insightful introduction and also kind of talking to us about the potential and challenges that comes with like the cardiac MRI data. So I hope you guys are ready. We'll be looking at the technical architecture that we have. And here in this like particular slide, you can see a bunch of things that we are doing, right? From basically what we are trying to target here is from data kind of collection to AI-assisted annotation to model development and finally like deployment on AWS. So what I'll do like next is I'll go through like each of the component one by one, and I'll talk about basically like the technologies that we've used. Right. So the first one is the data collection. So we collected our data set from all across Northwestern medicine, across Chicago. One of the major and important step that we had to do was the data de-identification, which was basically like Dr. Kline's own pixel guard, which was around like 100% accurate for our case. Second is annotation. And we know annotations are important and for all of the reports that we generate as well. We integrated Monai label, which is the AI-assisted annotation, with AWS, basically with 3D slicer on AWS. Next, as we mentioned, annotated data is kind of time-consuming and it's kind of expensive. We went with like self-supervised learning architecture, and what we did here was the self-supervised learning architecture was divided into two main architectures. One where we use the unlabeled data, we learned like rich features of that unlabeled data, and then we transfer those like weights for further like fine-tuning our segmentation downstream model. Post our model development and validation, we deployed this particular on AWS. For this, we used Docker containers, NVIDIA Triton Inference Server, TensorRT, and AWS Lambda functions, so as to accommodate if like a new patient like basically comes in, the model should be able to kind of run and get us like the final results. Okay, now that we've looked at the solution architecture, we'll talk about one of the main things, that is data, right? AI in medical imaging has actually kind of improved a lot in the coming years, right? But there are still a lot of like challenges. One of the major challenge is basically data de-identification, and one of the reason is because patient data is sensitive. Right? And there are a lot of like rules. So there's a need for data de-identification, and because there are like metadata where the PHI information can be there, and also like sometimes there are burn-in pixels on the imaging. So that makes it more difficult and more time consuming because you have to like go through each and every data to actually do that. So again, we used Dr. Kline's pixel guard for that. Second is having correct annotations. So we collaborated with bunch of kind of radiologists and cardiologists like all over. One was like Northwestern Medicine in Chicago, some of the institutions from Michigan, and also some people from Australia, so that we have like a diverse set of annotations. And we also had like peer-to-peer review to have like much better annotations. And we used Monai label for that with AI-assisted annotation. Finally, we have metadata selection as well. As we know, metadata is equally important, like which year the study was from, magnetic click strength, pixel spacing, and a lot more. To improve basically our post annotation, we employed simple yet like very effective technique of median filtering. Disjoint like regions were replaced by nearest neighbors, and kind of eliminated like small problems that like pixels which might have been due to like human error. Right? Now that we've looked at all of the data, now comes the exciting part. That is the model, which is, as we mentioned before, we were using self-supervised learning, right? So what self-supervised learning here is, we are actually using an unlabeled image, and we are trying to basically like learn the rich features that are there in the image. And you can see from the image right there in the augmentations, the before, that's that's the target value that we are trying to achieve. What we do is we actually add random noise, like random different cutouts of like noise. So, and we ask the model to basically reconstruct that image back. That's where it's trying to like learn those specific like reconstructed part. We used 1,500 images because we tried different 5,000, 10,000, did not have like considerable amount of improvement. So we stuck with like 1,500. As we know, self-supervised learning is kind of works best when using like different set of augmentations, specifically for invariance, for different set like rotations, and also elastic deformation if there is any problem in the heart. And finally, like all of the like cutouts and like reconstruction that we are trying to do. We evaluated various MONAI-based like models, 2D, 3D, CNNs, and transformer. But due to availability of large number of unlabeled data, which was 1,500, we went with transformer model. But as we like spoke, we have less number of annotated data. We went with like the 2D structure so as to avoid any problems, basically. And finally, loss optimization. We did like speak about reconstructing the entire image. So we use like reconstruction loss and also contrastive loss to have like similar images in like the similar plane. Okay? So now that we've looked at the self-supervised learning architecture, we'll just look at the quick results that we have. And we're just showing here Cine2s and Cine Sacs. The ground truth image, as I showed earlier, we have like the transform image, which goes into the model. And you can clearly see from the model output that the model was able to reconstruct the image. There was a lot of experimentation involved in invariance, like adjusting the transformations. Similarly, like with SAX as well. Now that we've like fully fine-tuned basically the self-supervised learning architecture, what we'll do is we'll transfer the weights of the self-supervised learning architecture into the supervised learning architecture. And you can see from the image bottom right is where you have input, you have VIT, decoder, and the segmentation, right? So here the VIT is the transferred weights that we have like from the we transfer from the self-supervised learning architecture. The radiologist contributed generously 50 images per image like view that we have with temporal, for 25 temporal slices. We were very careful with data augmentation because we did not want it to like kind of have any problems with the model that was trained on like self-supervised learning. So we had to use very mild augmentations. And I did forgot to like let you guys know that we used MONAI's like inbuilt transformations, and as like MONAI is open source, we were able to add like some custom augmentations to use like pixel spacing in the pixel spacing and like the way we kind of like input the entire like image. As said before, we're using 2D unitar transformer model as we have only 50 annotation images per view. And finally, we used multiple different loss functions. As you know, we have 6 different views. There were a bunch of experimentations involved when trying to understand how many labels we have, if there are like combinations of big labels or like more kind of area or less area, and also like some of them, particularly like SAX, the boundary was a lot important. So we had to use kind of boundary loss as well. Most commonly, focal, dice, and C worked a lot better for us for most applications. So similar to self-supervised learning, we'll be kind of going through like some of the examples of the output images that we have. And we have input plus ground truth on Cine 4s, Cine 3s, and Cine 2s. And we have like image plus predicted image. And you can see it kind of works a lot better because of the way we view self-supervised learning and basically like 50 annotated images. Now that we've done all of this segmentation and we've got like proper results, like left ventricle mass, and we calculated the area per pixel, and basically like using bunch of metadata information, we calculated how much blood is actually pumping, and a kind of comprehensive report is generated based on like from the inputs from the cardiologist, radiologist, and the head of cardiac surgery. We have like here Dr. Johnston. Thank you again. After that, we have like a summary of each and every kind of report. So basically, you can see the normal range, what the normal range is. So it will basically kind of theorize like the entire report, right? We still have like more stuff coming in. We'll generate kind of an entire report from images using like LLMs and VLMs, as Dr. Kline was saying. So this is my final slide. I'll give back to like Dr. Kline for a more exciting part, that is the UI. I hope you guys enjoy. Thank you.
Thank you, Chinmay. All right, so I get to do the next part, so the road ahead. So does everybody actually want to see the UI and see what we build? Somebody say yes, I don't come up here for fun. Okay, great. Well, I think Chinmay teed this up really well with the self-supervised learning components of this, but, and you could see from the reporting kind of slide that he had before it was that it directs those numbers and outputs and then actually creates a report that becomes actionable. But that's still not enough for me. I always want more. So I wanted to make these models and this solution work in a synergistic way between man and machine. So here we go. So you can see Chinmay is going to sign in here. This is all running on cloud architecture. So you can see kind of we're going into the cardiac MRI variant of this, and we land on a patient list that would normally occur in a radiology workflow. So while it's great to run a lot of these kind of models on batch and try to find patients that might be at risk or that we want to get into the clinic, we also wanted to build this UI and this whole tool so that it can actually integrate into the clinical workflow. So you can see all the different kinds of views we have here. And this is the exciting part, is that you can actually see the clinician being able to now edit where those segmentation boundaries are. So this is where those metrics that you saw on that output slide are actually going to be editable maps that now feed into that report, that if you change them, the report will update in kind, as well as we can have some back-end fun processing where we're going to continue to learn and train on those items. If the solution missed a label, for example, you can add that back in too. And then going into the info section, like Chinmay showed on the other slide, was that we actually have those numbers, and those are going to update accordingly, as well as it'll output a particular report, which now we can edit and add text as necessary. And yeah, so that's our UI.
Hi, my name is James Carr. I'm a cardiovascular radiologist and chair of radiology at Northwestern University Feinberg School of Medicine in Chicago. Northwestern has one of the busiest cardiac MR practices in the world, and we do a lot of innovative technical development in the imaging research space. Cardiac MRI is an essential tool for diagnosing heart disease, especially cardiomyopathies. And image quantification of these cardiac MR images is essential for determining cardiac function and volume, and this is a very important part of making these diagnoses. I've been a part of Project Corazon for the last several months, and I've been extremely impressed by how accurately and quickly this tool measures cardiac functional parameters. It is very easy to use and can provide quantitative results in line in an automated manner. It is particularly innovative by being able to produce anatomic maps nearly instantaneously, which really simplifies the workflow. I'm excited by the future of this project, as its capability can be extended to measuring other physiologic values such as flow and also assessing scar within the cardiac myocardium. This tool may also be extended to other imaging modalities such as CT and ultrasound, providing an across-the-board assessment of cardiac pathology. And I'm fully committed to supporting the development of AI technology in medicine, as I believe it can greatly support and enhance clinical work.
I'm Doug Johnston, the Chief of Cardiac Surgery here at Northwestern Medicine in Chicago. I'm standing outside our cardiac operating room 33 here, where a young patient is about to undergo a life-saving procedure. The reason we know what is wrong with her heart, and as importantly, what we need to do to fix it, is because of the quality medical imaging she received. Having accurate medical imaging is critical to the management of patients with cardiac disease. Not only does it tell us where a patient is in the stage of their disease, whether they have a diagnosis that may be associated, like hypertrophic cardiomyopathy, with sudden death, which in a young patient obviously is devastating and incredibly important we find out what's going on and when. But in order for us to know what to do, we have to have not only a diagnosis, an understanding of what the physiology is, but very accurate measurements, which we can take on high quality medical images like an MRI like this. Not every study is done in a way that lets us get there easily, and that's why we're so excited about the work that's being done to automate assessment of these images by the AI team in the Kline Lab.
I think my remarks on. Okay, great. So you got to hear from our clinical partners. I thought that was really important. So these are a couple of my collaborators back at the university. Dr. Johnston, our chief of cardiac surgery, who's actually here in the audience with us today, if anybody wants a consult. But it's important, I think, to obviously collaborate with our clinicians tightly so that we make sure we're building something of value, as well as that at the end of the day, even though I went to medical school, I still am just a lowly engineer. So it's worthwhile hearing from people who know better. So up next for us is that we want to start to stress test this tool. So this means validating this tool with other data sets, retrospective data, comparing our outputs with reported metrics as well. And we have to do this in collaboration with hospitals and research institutions. So we're trying to partner with other researchers around our own university as well as outside and the NIH. And then this is really what's going to form the backbone of our ability to get this move through the regulatory approval roadmap, i.e. FDA. And again, if I haven't given you the sense that I want to build solutions that really truly work, is that I also want these models to evolve and increase accuracy as time goes on. So as you saw, we allow for those expert corrections by radiologists in that workflow. And so by incorporating human in the loop kind of reinforcement retraining is that our models are only ever going to get better. And if clinical practices change or imaging techniques change, is that we're going to be able to account for that as time goes on, because we all, I think, can know the problems associated with model drift and model decay over time. So we believe in an AI evolution where we can only get better accuracy and consistency. And it's tools like this that I think are really going to allow us to standardize clinical care practice across the board so that things run very efficiently in the cloud, so that, from the point in time where we have a patient scanned at the radiology reading room, and then the scan is processed in the cloud before the radiology actually gets to it in that workflow list. And when we have these models kind of running in the background, even before the readers have looked at them, we can also start to try to flag, out of bound items. So if this was a really sick patient, maybe we want to move that to the top of the chronological list. That kind of technology isn't available right now. Expanding on this, so obviously as a continuation of our roadmap, we want to continue to integrate with hospital systems and imaging systems, so merging our PACS systems with the power and scalability of the cloud so that all you need is an internet connection to be able to run these kinds of powerful models and be able to serve your patients. We're already very hard at work in my lab at the university, expanding this, as you probably saw in the little lead-in UI component. So although this project is, mostly focused around cardiac MRI, the technology showcased here is already being expanded upon to create basically a multimodal cardiac imaging suite, where we are starting to fold in models with regards to CT, ultrasound, X-ray angiography. And then moreover, I want to really, ultimately, I think this fits in a real workflow process where we think about an end-to-end healthcare delivery pipeline. So this includes the de-identification that Chinmay kind of said, where we can de-identify images and share them across to other institutions or sites that might have this tool kind of implemented, where we can standardize the approach across imaging types and across institutions to better serve and democratize high-end care. We want quality assurance metrics. So I don't want my machine learning models looking at bad images. Neither do I want my radiologist looking at a bad image. So I want to create models that can act as a filter mechanism before my models even see this stuff. Following that up, I think obviously you started to see kind of the diagnostic suite of things being built out, but we can also start to leverage other types of agentic workflows for things like billing automation from these outputs as well. And one of the things that Chinmay mentioned that we're also kind of excited to debut and showcase here in this talk is that tool called PixelGuard. So this was kind of developed, and although not specific to this project, was used in this, and it includes medical data de-identification. So this is really a tool specific to medical imaging, which can redact, can swap out both metadata and pixel data. And the idea is that this is going to actually, this part of the tool and framework that we've are showcasing here a little bit is hopefully going to be available to you next week on AWS Marketplace. And this is another kind of undertaking with my lab and another cloud team. So this is made in conjunction with Scale Capacity, some of which I think are also here today. And the hope is that by deploying this is that we can not only enable our own workflows this way and build more amazing tools, but this in and of itself allows the creation of more tools like the ones you're just seeing today. So it might be Chinmay and I up here talking about this with you guys, but nothing is done in a silo. So there are many partners and contributors and team members that went into this, and we want to recognize the very multifaceted team across kind of cloud and software and GPUs and hardware and clinical expertise that went into this project. So it's a big thank you to them, and thank you for listening. And I think we're happy to take questions.
Thank you so much. That was great. Do we have any questions? Okay.
Thank you. I apologize to the crowd. I have several. Was this, I think you mentioned it, but I want to just clarify, was this unsupervised or supervised learning?
Self-supervised learning.
Okay. And was this was just Northwestern's data
Yes.
that it was trained on?
Yes.
How confident are you in the reproducibility of this model?
So, meaning, as we know, usually different kind of, if basically the image is coming from a totally different source, there can be some noise or something can be included. So if you remove that and if the image is clean, I think, yeah, it can actually work the way, say, the results that we've shown.
In that, I assume then that's the sort of next phase is sort of test.
Exactly, yeah. So we actually are just about to start some work with another researcher who has, so although this was a single site data set across, I think it was 15 years worth of data, right, sampled across. So we kind of do have a fairly well, and Northwestern itself has a fairly large catchment pool, which means we already have a fairly diverse data set. That said, obviously, like you've pointed out, is that it's worthwhile making sure that it's very robust. So there's a data set for some of these models that we actually found out a researcher has that with the segmentation maps and things, and from it comprises something like over 800 patients or so that has clinical outcomes and from 62 different sites. So that's going to form a lot of the backbone of the validation.
And also just wanted to add, we also have some colleagues Michigan and Australia,
Yes.
which we'll also kind of experiment on.
Well, first of all, congratulations. What you've made is very hard. And I know you guys know that. Not everybody in the field, in this audience, may know quite how hard what it is that you've done. So that's fantastic. Last question. Do you see yourselves as the agency that's going to go after regulatory approval for this tool?
That's a me question, I think. Yes, absolutely. So as part of the, although I run a lab out of the university side of things, I actually do have a startup kind of mentioned here, and it's not supposed to be a pitch for that at all, but it is part of the NVIDIA Inception program where this, as well as some of the other monetizable deployments out of the lab, can be commercialized and scaled quite quickly, where that's the entity that's going to be able to take it forward and scale and commercialize with it. That said, I think there's a lot of research-based stuff we want to be able to do first, which is going to form the kind of crux of the submissions in terms of papers and clinical approvals for that FDA roadmap.
And also, if I can go back to your first question, right? So if you saw our UI actually worked was where kind of the radiologist can actually go and kind of edit all of those. So there is a pipeline that we are thinking in the future, which will kind of use that and kind of retrain an MLOps pipeline. but I'll also like use as an autosec 3D because we'll have like more number of like annotated data. So instead of just using 2D transformers, we'll use 2D and like 3D, and based on that, whichever like performs the best, we can actually use that. So it can be actually like used, and yes, we are like kind of pretty confident based on the amount of data that we have. I think I didn't mention it was from 2005 to 2024. So we did like use a little less from 2005 to 17 because it was an old data. So maybe like around 35%. Majority we try to like use as close as possible.
Excellent. Do we have any other questions? Yeah.
Thank you for a great talk. Again, very impressive work. Sorry, I might have missed that. Did you actually like integrate with the packs and are able to actually run that algorithm once the data is coming out of the packs? You showed a great UI, but I didn't know, is that what the clinicians are actually using, or?
They're not using that right now yet. Yeah, so that whole framework right now exists in the framework of the cloud, and then but we're in the process of like wanting to integrate with like the cloud, the packs to cloud kind of transition. Yes.
Okay, so you are manually like uploading that to the cloud, triggering the algorithm, and then
Correct. Right now, that is, yeah, that's exactly it. Yeah, that's why it's part of the roadmap.
Okay, great work. Thank you.
And also just making sure AWS Lambda function is triggering. Just making sure.
I'm sorry?
AWS Lambda function is actually triggering.
Once it's uploaded, yeah.
Congratulations on what you guys built. On the annotation tool, you were using an in-house built annotation tool? Or like, can you talk through that architectural decision rather than like a RoboFlow, or how you decided on that?
Sure. So at the start, the one that I like, the architecture that I showed, we were using Monai's AI assistant toolkit, right? It was using it with 3D Slicer on AWS, which was because we had like remote annotators, so we had to like kind of get access to them through cloud. And also some of them were on the same VPN, so we were able to like do it on-prem. So the other one was an inbuilt, the one that you saw on UI, that is kind of like an homegrown annotation like tool that we have. So it's totally separate from what is 3D Slicer or like.
And that was to optimize it? That's why you used in homegrown versus a packaged one?
Yes, we actually like wanted to make it user friendly. So instead of like trying to open a different application, I'll be using that in the same UI, right? Or else like if 3D Slicer, it's a separate application. So it will make a lot of efforts, and then the data has to be kind of shifted to location, and then it has to like be re-pulled. Instead, we actually did it in the same canvas that we were building for like the UI.
Thank you.
And just I think to expand on that, because I mean, we use 3D Slicer to get the annotations in order to train this for all the different masks and things. But there's another one called CVAT that we also use for some other work ongoing. But I think I can speak for the frustration I heard from clinicians and clinical partners in that 3D, the kind of mechanism for editing those maps, whether it was 3D Slicer or CVAT, is very mixed reviews. I think. I mean, it's one thing that those exist for kind of the development of research projects, but are not really well kind of integrated into that like review type workflow, like I think you saw. So that was the need to, I think, drive these editable maps, but still have that ability to port that over to various other kinds of imaging modalities as well.
Thank you.
I just had a quick question on kind of outliers. You kind of touched on, data quality and your data sets.
Yeah.
Did you end up collecting any kind of outlier data, quality of images, minimal certain this and that, and did you end up training on that, or are you trying to stick to a certain quality of data set as a requirement for your input?
We actually did a combination of that. So as I said, we had almost 100,000 data. Out of those, we selected like 1,500 for each. We also had 10,000 for each as well. So we tried to kind of go through the data as much as we can. We might have like missed some of them, but I just wanted to include those just in case like there is a possibility in the future that might happen.
Like
so
a
we're doing
diversification.
very slight number, I would like to say.
So you diversified your data sets for, real world scenarios,
Exactly.
for real outcomes. Okay. Okay, cool.
Yeah.
Yeah, I think that was part of the reason for sampling across to kind of temporally, as well as the number of slices that occurred, or the scanner type it occurred on. So we wanted to make sure that as much diversity as we could was kind of embedded in our, although single site, as diverse as we could be within a single site's data set.
Got it. Thank you.
And so I think we were able to, we trained, I think, on like the kind of 15,000 for the self-supervised component, but we had 42,000 to pick from.
Yep.
Got it. Thank you.
Anyone else? All right. Can you ask you very last questions? I think we're running out of time slowly. Can you tell us a bit more about computational resources utilized for training the models? And
Yes, so much.
Yeah, so we used a combination of on-prem and AWS-like systems. For on-prem, we used H100s, 4 H100s, and on basically like AWS, we used also L40s, we used A100s, and for AI-assisted annotation, we were using L4s.
okay, perfect. Thank you so much. Thank you for your talk, and thank you for being part of the session. Enjoy the
Thank
rest
you so
of
much,
the GTC.
everybody. Thank you.